Welcome back, everybody. So today we're going to talk about how you can graph sine and cosine functions. Now, we've looked at graphing things like y equals sine x and y equals cosine x before. But what we want to look at today are the different kinds of transformations that you can get on these sine and cosine functions. Because a lot of times, actually, it turns out that we want to look at graphs of transformations of sine and cosine. So, just like any other function, you can do any transformation that you want to with sines and cosines. It turns out, actually, that the properties of sine and cosine make them kind of easier in some ways to deal with these transformations. And the reason is because of the fact that these are periodic. And they have a period, if you remember, of 2 pi. In other words, they repeat themselves every 2 pi. Well, the fact that they're periodic makes graphing them kind of nice because it means that once you graph them over one period, everything else is just going to be a copy of that shifted along the x-axis. Now, when we graph something like, let's just start off with sine x. If I were to graph y equals sine x, we've seen what this looks like before by thinking about the unit circle. And so what you get with this sort of thing, if I have my axes here, and let's say that here I have 2 pi, here's pi, pi over 2, 3 pi over 2, let's put -1 down here and 1 up here. So the sine function starts at 0, it goes up to 1, it comes back down to 0 at pi. Sorry, that should be kind of symmetric looking here. It comes down to -1 at 3 pi over 2, and then it comes back up to 2 pi. And then it's going to just keep on repeating itself in this same pattern all the way out. So if we go up to 3 pi and then 4 pi, well, it's going to be the same pattern here. And if I start moving off towards the left here, again, the same pattern is going to just keep on repeating itself. So we get this same wave pattern going off in both directions forever. And really, all that matters is that I graph it over one interval whose width is equal to the period. Now, when we want to do transformations on this kind of thing, well, there's a bunch of different transformations that you can do to functions in general. And those are the kinds of transformations that we're going to be dealing with sines and cosines. Oh, and remember, I should mention here that for the cosine graph looks just like this, except it's been shifted to the left by pi over 2. So it starts at 1, it comes down, hits -1, and comes back up to 1 when you get back to 2 pi. But otherwise, it's actually the same shape as the sine graph. So the first kinds of transformations that we're going to think about are going to be the ones that are kind of the easiest to see what happens. And maybe the easiest thing to see what happens is what happens if you just multiply one of your trig functions by some constant out front. So what if I wanted to graph something like y equals 3 times the cosine of x? Well, when you multiply something by a constant like that, all that does is it's going to scale things vertically. So, give me a moment here to mark off some important points on this axis. If we start off with the graph of cosine x, we would get something that looks like this over one period. And if I multiply that by 3, all that's going to do is it's going to stretch things by a factor of 3. In other words, it's going to, now instead of starting at 1, it would start up at 3. and instead of going down to -1, it would go down to -3. But otherwise, it would keep the same basic shape. So let me mark those points where they've gone, and then we will connect them up with this wavy line shape. Whoops, that was a little high. There we go. We'll put it down there. Okay, so we get this kind of a shape. And this is now going to just keep on repeating itself forever. So as we go out to, let's say, 3 pi, okay, this thing is going to come back down to -3 here, and then it's going to keep on coming back upwards and hit +3 again out here at 4 pi. And if we went off in the other direction, it would do the same kind of thing, okay? It's just going to keep on repeating this same pattern. That's because it's periodic, meaning that it keeps on repeating itself. And so we really get the same graph. It's just that we've changed how big this wavy pattern is. Instead of going from +1 to -1, it goes from +3 down to -3. Now, this is true for any kind of a graph of any kind of a function. If I multiply it by a constant, all it's going to do is it's going to give me a vertical stretch or a vertical shrink. If it's a number that's between 0 and 1, then it's going to shrink things. So when we are graphing one of these functions, this number out front, when we're talking about trig functions, sine and cosine, this is called the amplitude. And the important thing about the amplitude is this. It tells you how tall the waves are going to be. So you can think of like, okay, every sine and cosine graph, which by the way, those graphs are called sinusoidal curves. I'll show you how to spell that. Sinusoidal curves. Every one of those is going to bounce back and forth between two numbers. Well, this total distance between those two numbers is always going to be twice the amplitude. Now, why do we think of it as twice the amplitude instead of just the amplitude? Well, it's because the amplitude is how much this thing got stretched. And normally we go between +1 and -1. If we change that to going between positive amplitude and negative amplitude, that actually gets us to twice the amplitude. And I dropped my pen. Have my pen back. Sorry about that. Okay, so that's why it's twice the amplitude and not the amplitude itself. So a bigger amplitude means that the waves are going to be taller. A small amplitude means that the waves are going to be small. So let's see if you can do a quick sketch of one like this. So I'm going to give you a problem here, ask you to pause your video, try to sketch this yourself, and then we'll come back and see how you do it. So see if you can sketch y equals 3/4 sine x. Okay, hopefully you were able to do that. Let's take a quick look at how you can go about making this graph. So I'll start off with my xy axes. We'll put pi over 2, pi, 3 pi over 2, 2 pi. Now, if I start off by just graphing the regular sine function, going from +1 to -1, then sine is going to start here at 0. It's going to go up to +1, come back to 0, go down to -1, and then come back to 0. And that gets me over one full period. So we would get our basic sinusoidal shape here going like this. But the amplitude here is 3/4. So this is y equals sine x, the original function. When I do this transformation, I'm changing the amplitude to 3/4. So I should now go from +3/4 to -3/4. Everything else remains basically the same. It's literally just that I'm changing how big these waves are. And if I wanted to keep on going with this, well, it's easy enough to do that because I literally just have to copy this same shape going off forever with the same height of the waves. So you can keep on going, make the graph as big as you want to, but it's always going to be the same picture over and over and over again. When you do these graphs of trig functions, then you want to start off by saying, okay, can I graph this over a single period? And then once I have it over a period, okay, now I can just start shifting things as much as I need to. All right, now let's look at another type of transformation that you can do here. This is going to be one where we can actually change the period. So let's think about what happens if I were to try to graph y equals the sine of, let's try doing pi times x. Well, in general, what's going to happen if you multiply the variable inside of a function by some constant? It's going to give me a horizontal stretching or shrinking. And the key point is this: if we originally repeat every 2 pi, so whenever x changes by 2 pi, we repeat, then if I multiplied x by pi, now we're going to repeat every 2 pi divided by pi, which is equal to 2. In other words, we're now going to keep on repeating ourselves, but instead of repeating ourselves over an interval of, or over intervals of 2 pi, now I'm going to start repeating myself over an interval of 2. In other words, the period is going to be different now. It's now going to have a period of 2, but it's going to be the same shape graph. And that means that I can make this graph very easily by just essentially graphing y equals sine x, except instead of graphing it with a period of 2 pi, I'm going to graph it with a period of 2. So halfway through, at the start of a cycle, I should be at 0. Halfway through, I should be at 0, and at the end of a cycle, I should be at 0. One cycle meaning basically an interval with a length of 1 period that kind of starts at the beginning. When we think about sine, we always think of starting at 0, going up, down, and then back to 0. Halfway between the first half, in other words, a quarter of the way through here, I should get up to positive 1. Halfway between the second 2 points, which is going to be at 3 halves here, I should be at negative 1. But the picture here that I get is going to be the same shape. And now I can just keep on going if I want to extend this. So I can say, okay, at negative 1, I would be back up to 0, and then I would come over and go over here. This would be at negative 2, and so on. And I could keep on going on the right-hand side as well. So multiplying the variable by a constant like this is just going to change the period. And what is the new period going to be? Well, we can write down a general rule for what is the new period by using the same kind of reasoning as we did in this problem that we just looked at, where we multiplied by pi. So in general, the period of y equals sine of omega x, this is supposed to be a Greek letter omega. I know it looks kind of like a W. That's why I sort of exaggerate the loopiness of it. If you see these printed, it's kind of obvious which one is which, because the W is very loopy, the omega is very loopy, the W is has sharp corners. But when I'm just writing, my W's kind of look a little bit like omegas. Anyway, this is supposed to be an omega. And this reasoning also works for y equals cosine of omega x. Well, what we want to know is when does omega x go from 0 to 2 pi? I guess that's not really a question the way that I wrote it. That is just what the new period is going to be. Okay, but when does omega x go from 0 to 2 pi? Well, omega x equals 0 when x is equal to 0, and it's going to equal 2 pi when is that going to be true? Can you solve that equation for x? Well, the answer is going to be that it is when x is equal to 2 pi divided by omega. So this is the new period. In other words, when you graph a function that looks like this form, and this is true for cosines as well as for sines, then the interval size that you get before this thing starts repeating itself is going to be 2 pi divided by this omega. Now, we can put this together with the amplitude thing. So, how do you graph something of the form y equals a sine omega x, or y equals a cosine omega x? And we will assume here that a is bigger than 0 just to make things easy on ourselves. Well, the answer is that this is the same shape as y equals sine x or cosine x. It just depends upon which one of these you're working with. Obviously, you have to use, if the original problem was in sine, then you have to use sine. If the original problem gave you a cosine, you have to use cosine. But it's otherwise very much the same kind of thing. Then the new things that you want to remember is that the new height goes from minus a to positive a, and, whoops, that's not how you spell height, I forgot my T, and the new period is the original period of 2 pi divided by this omega that's multiplying the constant. So this gives us a really nice way of very quickly making these kinds of graphs. So make sure that you have this noted down, and now we're going to look at an example of using this. So let's suppose now that I want to graph y equals 2 times the cosine of 4 pi times x. Okay, the things that I'm going to note down here are that the amplitude, remember the amplitude is just this factor out front, is going to be 2. And the new period is going to be the original period of 2 pi divided by this 4 pi factor that is multiplying the x. Well, that simplifies to 1/2. So our new period is 1/2. And that means I can make my graph, possibly because I have trouble drawing straight lines. Here's x, here's y. It's going to give me something that is the same shape as the cosine graph. However, the new height is going to go between positive 2 and minus 2, and the period is going to be 1/2. Now, I need to mark out some place that is halfway through the period, so in this case, that's going to be at 1/4, and then I need to mark out at 1/4 of the way through the period and 3/4 of the way through the period. So that's going to be at, in this case, 1/8 and 3/8. and we start, whoops, I'm sorry, we're doing cosine, not sine. So we don't start at 0. I was thinking of sine in my head there. We start at the top for cosine, come down through 0, 1/4 of the way through. We go to the bottom, halfway through, back to 0, and then we hit the top at the end. So we get the same shape as ever. It's all that is changed here really is basically how I've labeled the axes. It's exactly the same shape as we would get if we were to just graph the cosine function by itself. And as usual, this is going to keep on going in the same pattern. So for example, out here, we are going to have hit 3/4 by the time we get to the bottom again, and keeping on going in this same kind of fashion. Just take this picture and keep shifting it horizontally to get everything else that you have. So when you're graphing these types of things, the important thing to do is to make sure that you have one period completely graphed in detail. And then you can kind of just sort of indicate how the rest of it goes, indicate that you know that this thing keeps on repeating itself forever. But yeah, I mean, that's really all it's doing. You don't have to show a lot of detail outside of that one period that you've shown. Now, there are two other things that we could potentially do to these functions in order to shift them around. So we can add a constant at the end, and we can add a constant inside the function itself. Adding a constant at the end is probably the easier thing to deal with, so let's take a look at that first. What if I wanted to just graph something like y equals sine x plus, let's say that I do sine x plus 1/2. Well, adding a constant to any function when I graph it, all that does is shift this thing vertically. Okay, so what is that going to do in this case? Well, the original sine function looks like this. It starts at 0, comes up, comes down, comes back to 0, and it keeps on going like this. Again, I'm not going to do a whole lot outside of this one period. We just kind of indicate that, yeah, we know that it keeps on periodically repeating here. And of course, you want to be able to make the rest of the graph in detail if that's needed, but you don't necessarily have to do that when you're just trying to sketch the basic idea. You want to start by sketching one period, and then if we need to, we can make as much of the graph as the problem requires. That looks like it's a little high here. I'm sorry. Again, keep in mind that I'm not an artist here. Well, if I shift everything by 1/2, here's what's going to happen. Normally, the midline here would be at 0. That's sort of where this thing crosses through the middle. The bottom would normally be down here at -1, and the top here would be at +1. Well, what adding half is going to do to this is it's going to shift all of these upwards by 1/2. So my middle line here is now going to be at 1/2. My maximums are going to be at 3/2, and my minimums will be at -1/2. But otherwise, we get the same picture. So this point gets shifted up, this point gets shifted up, and this point gets shifted up. That point gets shifted up. I didn't shift this point, did I? There we go. That point also gets shifted up. So everything has been shifted up by 1/2. Excuse me. Sorry about that sneeze. But otherwise, the picture looks just the same as it ever did. Everything just got shifted. And that is really all that one of these constants on the end is going to do to one of these graphs. It's just going to shift it vertically. So you take your original center line and you shift it. You take your original maximum and you shift it. You take your original minimum and you shift it. Make sense? Now, the thing is, that's going to work even if the amplitude isn't 1. So I gave you this example where the amplitude is 1, just to start off with something relatively simple. But the same idea is going to work if I have some other kind of amplitude. So the rule is, if I want to graph y equals a sine x plus b, or y equals a cosine x plus b, then the rule is the new center line is going to be y equals b. The new maximums are going to be at y equals b plus the amplitude. And we're going to assume here that a is bigger than 0. We want the amplitude to be a positive number. And the new minimums are going to be at y equals b minus a. So we have the center line, we have the maximum, and we have the minimums, and otherwise this picture is going to be exactly the same as it ever was. So I want you guys to take a minute and see if you can use this to figure out how would you graph y equals 2 cosine x minus 1. And then in a moment here, we'll work it out together. Okay. Well, the way that we're going to do this is I'm going to make my graph here. Here's my x-axis, here's my y-axis. My new center line is going to be at -1. So I'm going to put a little dotted line here at -1. That's going to be my center line. Now the amplitude here is 2. So my new maximum will be -1 plus 2, which is +1. So that's going to be my new maximum, and my new minimum is going to be -1 minus 2. Well, that's going to be at -3. Okay, I didn't change the period or anything like that, so we don't have to worry about changing the periods. In other words, we're still going to go from 0 up to 2 pi. So let me just mark in those points here really quickly. Remember that the important points that we want to mark are going to be the full period, half of the period, a quarter of the period, and 3/4 of the period. Those are sort of the important points to keep in mind when you're graphing sines and cosines. Just like back when we talked about exponential functions, we had these important points that we wanted to keep in mind. Well, sines and cosines kind of have the same deal. Okay, so we're dealing with a cosine here, and that is important because it means that we start at the maximum, and then we're going to come down through the center line at 1/4 of the way through the period. We hit the bottom halfway through the period, center line at 3/4, and back to maximum after 1 full period. And now I'm just going to connect up these things using a nice sinusoidal curve. And there is 1 period of my graph. And of course, this is going to keep on going. So like over here, this is going to, that's kind of too, I started fattening this thing too much. There we go. So this is going to be at like 5 pi over 2, because if I shift everything over, 2 pi plus pi over 2 gets me to 5 pi over 2. And we're back at the center line. And of course, it keeps on going. We can keep going in both directions. Now, the most complicated kind of change that we can make to these types of graphs is what is known as a phase shift. So let me tell you what a phase shift is. This is what's going to happen when the start of the period itself gets moved. Normally, when we think of graphing sines and cosines, the nice thing about sine and cosine is that they start one cycle when x is equal to 0. If you start when x is equal to 0, well, that is a particularly nice thing for us in terms of the graph. We just start everything at 0, which is at the y-axis, makes things nice and simple. A phase shift is going to change all of that. So what does a phase shift look like? Let's suppose that I were to graph something like y is equal to the sine of x plus pi over 4. Just to give an example of the kinds of things that we're going to be dealing with here. If I want to graph something like this, well, where is the period going to start? So one period is going to go from x plus pi over 4 equals 0 to x plus pi over 4 equals 2 pi. Because sine goes from 0 to 2 pi in one period. And so what we're interested in is not when does the variable hit 0 and 2 pi. We're really interested in when does all of this stuff inside of sine go to 0 and when does it go to 2 pi. Well, that's going to be 0 at x equals negative pi over 4, and it's going to be 2 pi at x equals 2 pi minus pi over 4 should be 7 pi over 4. So what does this mean for our graph? Well, all it means is that everything is going to get shifted to the left by minus pi over 4. In other words, we start a cycle at x equals minus pi over 4. But otherwise, everything is going to be the same shape. It's just been shifted. So what is that going to look like? Well, if I shift the entire cycle to the left by minus pi over 4, then I'm going to start at minus pi over 4, and the full cycle is going to go up to 7 pi over 4. Let's see if I can manage that. 1, 2. Now, halfway through the cycle, instead of being at pi, is now going to be at 3 pi over 4. A quarter of the way through the cycle is now going to be at pi over 4. And 3/4 of the way through the cycle will be at 5 pi over 4. So I've still taken my cycle and I've broken it up into quarters here. And we're graphing a sine function. So we're still going to go between -1 and +1. We're still going to start at 0, hit the maximum 1/4 of the way, back to 0 halfway through, hit the bottom at the 3/4 of one cycle mark, and then we come back up to 0. So we get this kind of a picture. And of course, it keeps on going in both directions. You know, we can keep on shifting this over by periods, by one length of the cycle, and we get the rest of the graph. So the phase shifting here, really what that means is we call it a phase shift because it actually moves the wave horizontally. If you think about this shape as kind of like a wave pattern, then it's shifting everything horizontally. And it turns out that this kind of thing is very important in various applications in physics and also in just generally analyzing mathematical stuff. It turns out that you can analyze a lot of things in terms of trig functions, and this phase shift can be really important. So that's where the name phase shift comes from. Actually, I think it really comes originally from physics when they used this to study the behavior of waves, but this is the name for it. Now, the thing is, you can get phase shifts combined with changes in the period. By the way, this is kind of a long video, so I do recommend that you guys take breaks in various places. You know, get up and pause this, walk around for a little bit. Make sure that you can stay focused at each point, basically. All right, so general phase shifts. Because what happens if we have not just a change to the phase, but also a change to the period. So what if I wanted to instead graph something of the form y equals the sine of omega x minus b, or y equals the cosine of omega x minus b? Well, the answer is that we get our cycle to begin when omega x minus b is equal to 0, and the cycle is going to end when omega x minus b is equal to 2 pi. That means that we are going to begin when x is equal to b divided by omega, and we are going to end when we hit x equals, let's see, 2 pi plus b divided by omega. Now, if you calculate the length of one cycle, it's still just going to be 2 pi divided by omega. Because if I take the end point minus the start point, I just am left with 2 pi over omega. So the length of one cycle is 2 pi over omega, but the cycle begins at x equals b divided by omega. And notice here the signs on b. So the original function has omega x minus b, and that makes the b positive down here. So you have to flip the sign here. But that's where you start, that's where you end. So let's take a look at using this kind of an idea to make a quick graph here. So let's suppose that I have to graph y is equal to the cosine of 2 pi x minus, let's say, 1/3. Well, the things that I want to know, remember, this length is basically the period. So the new period is going to be 2 pi divided by this coefficient here, which is 2 pi. So the new period is going to be 1. And the cycle is going to start at b divided by omega. Now my b in this case is 1/3, so we're going to get our start at 1/3 divided by 2 pi, and that comes out to be 1 over 6 pi. So that means that we are going to have the following kind of graph. We're going to start the cycle at 1 over 6 pi, and it's going to end at 1 over 6 pi plus 1, which is the full period. Now, halfway through the period, then, is going to be 1 over 6 pi plus 1/2. A quarter of the way through the period would be 1 over 6 pi plus 1/4. And 3/4 of the way through the period would be 1 over 6 pi plus 3/4. This is a cosine, so it is going to start at the top at 1. It's going to come down through the middle 1/4 of the way. Going to hit the bottom halfway through, back up through the middle at 3/4 of the way through, and back to the top at the end of the period. It's a lot to put together here. But the nice thing is that because this is periodic, everything is now just going to keep on repeating itself. The other nice thing is that because these have these nice points, we don't really need to worry too much about what does this thing look like when it gets stretched or squeezed or anything like that. it always has the same sinusoidal shape. It's really just a question of labeling the axis correctly and making sure that you start the cycle at the correct point. And that's all that you really have to worry about. Now, this is a good spot to maybe pause this for a minute, take a little break, and then we're going to put all of these things together and give the general rule for how do you graph a general sine or cosine function. All right. The general sine and cosine functions are going to look like this. So you might have y equals a times the sine of omega x minus, let's call it phi instead of b, since I want to use the b out here. Or we could have a cosine omega x minus phi plus b. Here are the rules for doing this. The new period is going to be 2 pi divided by omega. The start of the period is going to be when omega x minus phi equals 0, and that is going to be when x is equal to phi divided by omega. The new center line is going to be at y equals b. The new maximum is going to be at y equals b plus the amplitude, and the new minimum is going to be at y equals b minus the amplitude. Okay, now this looks like a lot to kind of memorize, but it's really it's the things that we've looked at in these individual examples where we only had some of these pieces. We've just taken all of that and we've kind of mashed it all together, okay? So it's a lot to keep track of, but it really is just the stuff that we've done before put together into one problem. The main thing that I'm going to suggest is, instead of just trying to memorize all of this, I think it's easier to kind of remember, why is all of this stuff true? Now, when it comes to the center line, the maximum and the minimum, I think that that's kind of, probably those are the ones that are easiest, at least for me, to see why is this true. Well, this is all true because we're shifting vertically by b, and that's going to shift my center line by b. The amplitude is whatever this a is, and so the new maximum is a above the center line. The new minimum is a below the center line. Well, that's b plus a and b minus a. Okay, so that's where these three come from. The new period comes from every time this thing repeats or changes by 2 pi, it repeats, I should say. So every time this changes by 2 pi, the function starts repeating itself. Well, that's going to happen every time x changes by 2 pi divided by omega, because we're multiplying the x by omega. So a change in x gets multiplied by an omega, and that changes the period. The hardest one to remember, for me at least, is where does the period start? Well, usually when I'm looking at one of these problems, I just ask myself, okay, what would I need to plug in order to get a 0 inside of the sine function or a 0 inside of the cosine function? That is going to be where the period starts. And in that way, I don't even really have to memorize this formula. I just ask myself, okay, how would I make this be equal to 0? That's going to be where the period is going to start. Now, of course, that comes out to be phi divided by omega, if we call this number here phi. By the way, this is a Greek lowercase phi. I believe we've seen that before, but I just want to remind you in case that's confusing. It just looks like a 0 with a slash through it. But once you have all of this information, you can just go ahead, you put all of this information into a graph, and everything gets shifted around according to this graph, but it's all the same shape according to this information. So let's take a look at actually using all of that stuff in a particular example. So let's say that I want to graph y equals 4 times the sine of, let's say, 3x plus 1, and then out here we're going to have a minus 2. Okay, so the new period, we can write down this information in any order that we want to, but I'm going to start with the period. Well, the period is going to be 2 pi divided by 3. So that's just 2 pi over 3. The new start of the period is going to be when 3x plus 1 equals 0. That's going to be at x is equal to minus 1/3. So we're going to start at minus 1/3. The new amplitude is going to be 4, and the new center line is going to be at y equals -2. So that means that the maximum, that's going to be at -2 plus 4, which is +2. And the minimum is going to be at -2 minus 4. That's going to be at -6. Okay. We haven't actually started graphing anything, but honestly, this is kind of everything that you need in order to do this problem. The actual graph now is going to be just make the right shape and ensure that you have everything at the correct places. So my new center line is going to be down here at -2. I like to put a little dotted line here on the center line just to make sure that I'm keeping track of where things are going. It helps, especially if you are artistically challenged like me, to have these dotted lines to help you out. Minimum is going to be down here. Whoops, not at -4. Why am I writing a -4? We want the minimum to be down at -6. So again, a dotted line down there just to help me out. And the new maximum is going to be at +2. So we're going to put a line there for our maximums. Now the period is going to start here at -1/3. And it's going to end at -1/3 plus 2 pi over 3. So here is the end of my period. Now, 2 pi over 3 minus 1/3, that's going to be 2 pi minus 1 over 3. And then we can figure out what is going to be halfway through this period. Well, half of the period would be 1 pi over 3, so that's going to be at pi over 3 minus 1/3, so that's going to be pi minus 1 divided by 3. 1/4 of the period would be 2 pi over 12, so that's pi over 6, so that's going to be pi minus 2 over 3, over 6, sorry. Pi minus 2 over 6 is going to be at 1/4 of the way, and 3/4 of the way through the period would be, let's see, so 3/4 of this would be, 3 times 2 is 6 pi over 12, so that would be pi over 2, so that's going to be at pi over 2 minus 1/3. And I'm not going to bother simplifying that into fractions. Okay, so we've split up the period into its 1/4, 1/2, and 3/4 places. And now we are dealing with sine, so that's going to start at the center line, goes up to its maximum at 1/4 of the way through, back through the center line, hits the bottom, and then comes back to the center line. And so we get this shape. And as usual, it keeps on going like this. Now, I'm not going to lie to you, these are complicated, long problems in one sense, but once you get the hang of them, they're not too bad. Because once you have the pattern, they all follow this pattern. You find the period. You find where does one period start. You find the amplitude and the center line, and using those, you find the maximum and the minimum. You draw the center line, the maximum, and the minimum onto your graph. You draw the start of your period and the end of the period, and then you break the thing up into its 1/4, 1/2, and 3/4 places through the period. And then it's really just a matter of putting in the correct shape into there, okay? So you ask yourself, are we dealing with sine or cosine? Sine starts at the center line, cosine starts at the top. Otherwise, all of these problems, they all give you the same shape. So that's kind of one of the nice things about graphing sines and cosines. It can seem kind of complicated, but really, everything is always going to give you the same shape, basically, in the end. All right, so I do want you guys to make sure to practice these. Now, I believe this stuff is covered in chapters 7.6 and 7.8 of your book, so make sure to review those, look at those examples, and watch the videos that they have in MyMathLab for these sections, because those are going to give you more examples to look at and kind of see how they do them and listen to their explanation, because sometimes one person's explanation might not make as much sense to you as someone else's. Maybe for some of these problems, my explanation might make more sense than theirs. Sometimes their explanation might click with you easier than mine does. So I think it's really good for you guys to kind of listen to different people explain how they think about it and how they do it. And in the end, hearing how different people think about it is going to help you think about it in more ways and is going to help you understand things better, even if you kind of already feel like you understand what you're doing. All right, I will talk to you guys soon.